Okay, so the next part of our lecture on kinetics of particles, and currently we are studying on work and energy. So the second part of it is something called conservation of energy. So by using the principles of conservation of energy, you can solve a lot of kinetics problem and also kinematics problem. So basically, energy, right? So energy is conserved. So if you have initial energy before a process, that same amount of energy will exist after the process. So energy is you cannot lose those energies. Those energies is lost due to some inefficiencies. So for example, in the beginning stage, if you have T1, which is kinetic energy, and V1, which is called potential energy. So this is in the first state. This is in the first state of all, and then if any process happens, the kinetic energy and potential energy in state 2 will be equal. So one might get higher, this one is probably slightly lower, and when it change to a certain state, maybe the kinetic energy will become slightly lower and the potential energy will become slightly higher. But the total sum, total amount of energies from the beginning until the end remains the same. So kinetic energy. So kinetic energy is something which is always related to velocity. So if your object is moving at a certain speed, it definitely will have something called kinetic energy. So which is it is half mass times velocity squared. So this is for something which is moving linearly. However, if your object is traveling at an angular velocity, you have to take into account the angular part of it. So for example, this one is, for example, you have a rolling body. This is a roda, and this roda is actually traveling linearly, and it's also rolling. It's rolling and rolling and rolling. So it has two things. One, it has linear kinetic energy, and another one, it has angular kinetic energy due to the rolling. So basically, it is the same. Only thing is, V is equal to omega r. For anything rotating, the velocity is equal to omega times r. Omega is angular velocity, r is the radius. So this part we will learn later on lah. So if V is equal to omega r, you can plug in lah. Half mv squared. So this one become half m omega squared r squared. So this is this one you can also rephrase it to be half mr squared omega squared. Mr squared is something called angular moment of inertia. Moment of inertia. Angular moment of inertia. This one, don't worry, we will learn later on. So if the body is just rotating, we use this one. This is for rotating body. Rotating at fixed location. So this one just rotate at a particular axis. Okay, this is on kinetic energy. Next, there will be something called potential energy. So potential energy, probably you've heard this before. Potential energy due to height change. So you have mass times gravity times h. So mgh. So h is the height lah, the height change. And finally, you have spring potential energy. This is due to the elongation. So you can either call S or you can call X. This is the same. You can either put the equation, some books will put half ks squared. So it's the same. It's a potential energy due to the spring. So half kx squared. X stands for elongation. So if you have a spring, original state is like this. If you press it, if you give a force, this thing becomes compressed. It has stored energy. So these are the typical things that you're going to see if you are dealing with problems of kinetics and kinematics. You can solve it using conservation of energy. So we are not leaving this formula. Summation of F is equal to MA. No, we are not leaving this formula. This formula works. This is an alternative. What is it? Alternative. You can solve sometimes problems, even complex problem, easily using conservation of energy. So this was what I was talking about in terms of rotation about a fixed axis. So if a body is rotating and rolling and rolling and rolling and but it is also traveling, it has these two things lah: translational and rotational kinetic energy. And one thing you have to take into account is something called parallel axis theorem. So parallel axis theorem we will also learn later on, or maybe you have done before, when you translate the distance between the center of gravity to the rotational. So we will revisit this one. Okay, this is one very important application. Let's say you are designing a roller coaster. So roller coaster is on top of a hill. It's very high. Let's say it is 20 meter high. So at point A, let's say this thing weighs 200 kilogram. This cut weighs 200 kilogram. You can find the potential energy. So V potential is equivalent to mgh. So 200 times 9.81 times height. What is the height? The height is 20 meter. Okay, this is 200 kilogram. So the energy that this thing has is a lot. So 200 times 20 times 9.81. 39240 joule. This is the energy that this cut has. So when the cut travels down, it will convert the energy from potential energy, or you can put as Vp. I think it's a better way to put it as PE only. Potential energy is converted into kinetic energy. So mgh now equivalents half mv squared. So all the energy here has been converted to kinetic energy. So you can find out what is the velocity here. Let's say now the cut is at location B. Oh no, let's just call it 1. From top of the hill at the bottom, you can find out what is this velocity. And does it have enough energy to make another swirling action? So can this car reach this position B? Does it have enough energy? And then the car reaches here, location number 2. What is V2? So this one is, what is V1? Original velocity here is 0 lah. And if it does make it, what is the maximum height it can make? And finally it reaches location number 3. If so, location number 3, what is V3? Is it still too fast or slow? If it's too fast, you need to design some sort of springs that can absorb the impact. So spring, do you still remember potential energy from spring, which is half kx squared, so that the final velocity will become 0. And if nothing is lost, you can design an ideal system and assume nothing is lost from friction, etc. So you can roughly calculate all this just by equating mgh is equal to half mv squared. So mass, same, eliminated. So gh is equal to half v squared. So you can find out what is the velocity for this cut going down. Another application. So let's say you've got this car. This is a car. It has potential energy. Let's say the car steered off course, and then it will run into all these water barrels. So you cannot put sand inside, right? It does not absorb impact properly. So normally you will put water. So kinetic energy from the car absorbing into all these water barrels. You can calculate how much of this car's kinetic energy, or how many water barrels do you need to put here. So crash barrels, one of the ways that you can reduce the injury in the car. Okay, so now it's time for us to do some exercise. So let's read exercise 7. 2 kilogram package leaves the conveyor belt at A. Okay, this is a conveyor belt. This is post laju. Original velocity is 1 meter per second. This is original velocity. And then it slides down. Slides down. So now your package is here. This is a conveyor belt. So this conveyor belt has its own velocity. So you need to determine what is the box VB I suppose, so that there will be no slipping. So the moment it drops down, it just travels nicely. Okay. So normal reaction force, no need to find this one yet. Just find out what is the velocity first. So it is very high, 4 meter. So let's write down the formula. What is the formula that we should use to make it less confusing? T1 and V1, or kinetic energy 1 plus potential energy 1. Either way, you can choose which one you do it. Stick to the books. T1 plus V1 equals T2 plus V2. This is the equation that we have. Okay, condition number 1. This is condition number 1. This is condition number 2. This is equals. Okay? The moment it drops is equals this one. So at location 1, it doesn't have any. Let's write it down. Half mv squared plus mgh. Is there any spring potential energy? No, there is nothing. This one becomes half mv squared plus mgh. There is no spring energy involved. So original velocity, it has its original velocity. Okay, so half mass will be cancelled out. If you look at this equation, mass. So mass basically can be cancelled out. How do I put that down? This one can be cancelled out, cancel out. You're going to be left with half v squared plus gh equals half v squared plus gh. You're going to be left with this one only. So half 1 squared plus gh, 9.81 times height 4 meter, half v squared plus 9.81. If we take the reference height is equal to 0 here, at this location height is equal to 0. So this one becomes 0. So what do we get for here? You get half lah, 0.5. This one, $39.24. (0.5 v squared plus 0). Okay, so velocity is equivalent to, remember to square root. So the velocity becomes 8.92 meter per second. Okay, correct kah? 8.92 meter per second. Alright, so we're done. So you can determine the velocity of this cart going down. Let's look at another problem. So this is a 2 kilogram pendulum. It is released from rest at, this is, velocity here is 0. Velocity here is 0. Determine the speed of the bob and the tension in the cord when the bob passes through its lowest position B. Okay. Sama je ni, macam I think it's the same. mgh is equal to half mv squared. I don't see any potential energy here. But if you want to do it properly, T1 plus V1 equals T2 plus V2. T1 0, V1 mgh, T2 half mv squared. V2 0. Yeah, same. The formula becomes GH is equal to half V squared. So GH is equal to half V squared. 2 GH square root equals to V. V becomes 2 times 9.81 times height 1.5 meter. $29.43. This is the velocity. Oh, we haven't. Yeah. Wrong, right? Wrong. We haven't square root. So we got to square root first. Square root 29.43 becomes 5.42 meter per second. 5.42. So this is the velocity, and you can also find what is the tension when it passes through. This one is equal to A normal. There is A normal and there is A tangential. A normal is equal to V squared over R. This one maybe you've not yet done any exercise on this one, but we can do it. Okay, let's put up this is 2 kilo. Let's put up another screen, white screen. Okay, you must remember this thing that we have learned before. Any object that travels on a curvature, it will have A tangential, and this is not so tangential. A tangential and A normal. This is the magnitude A. So A tangential is the normal acceleration that we learn. A normal is equal to V squared over R. So if you were to calculate this one with the object here, the curvature movement, there is something called F is equal to MA. Yes. Now F normal is equal to MA normal. So now A normal becomes this one. So you plug it in. M V squared over R. This is F normal. So this is tension. This is mg. Since it's rotating this way, this is your A normal positive. So let's solve this equation. This one. So F normal is equal to mv squared over R. You have to find summation as usual. So going up is positive. What happens now? T minus mg is equal to m v squared over R. This is the equation. So what can we do here? Remember the radius is actually 1.5 meter. A normal going up, so 30 minus, what is the weight? 2 kilo kah? 2 times 9.81 equals 2 kali 5.42 squared bagi radius 1.5. So dapat T lah. Okay, let's calculate. Bahagi. Okay, this one radius no squared. No. Like that. V only squared. Okay. Squared. Bahagi 1.5 kali 2. You're gonna get 39.24. Okay, and then plus this one. 2 times 9.81. 2 times 9.81. 19.62. So it becomes plus 39.24. So tension of the cable is actually 58.86 Newton. This is the tension of the cable. Which formula does it come from? Same thing. F is equal to MA also. Only thing you gotta know is this one now, V squared over R. Remember, when your object moves here, A normal change direction. A tangential same lah. A tangential here. A normal now is like this. This is the magnitude of your acceleration. Okay, so this one is the explanation for this part. This value. Okay, next question. We are on a roll. What is this? Somebody bungee jumping. Bungee jump. Okay. 75 kilogram man. Bungee jumps. This is the sort of calculation that the bungee jump instructor has to know. Even though, yeah, normally all these extreme sports, you need very technical skills people lah. You need engineers to make sure all these things are safe. 75 kilogram man jump from a bridge. Initial downward speed, meaning he jumps he does not drop. He jumps at 1.5 meter per second. Determine the required unstretched length of the elastic cord to which he is attached to the order so that he stops momentarily just above the surface of the water. Wow. So he's gonna be here. Like that. At location B, VB is equal to 0. Otherwise he's gonna die with a lot of blood if his velocity here is not 0. Now you've got stiffness elastic cord is 3 kilonewton per meter. So remember back, you have T1 plus V1 equals T2 plus V2. This is kinetic energy, this is potential energy. This is kinetic energy, this is potential energy. So can you guys do this? Let's try. Half mv squared. Okay, it has kinetic energy. Potential energy is a lot, mgh. So half kx squared. This is spring. So if the spring is unstretched, so elongation of the spring is equal to 0, then okay lah, this part will be equal to 0 lah. So finally, so this part is actually still 0 lah. So final velocity kinetic energy becomes 0 lah, right? Setengah mv squared plus mgh plus half kx squared. So now let's take a look at the things which is going to be 0. Final velocity is equal to 0. Final height, we take h is equal to 0 here. Okay, final height is equal to 0. H is equal to 0. You're going to have this one. How about this part? This is 0. X is equal to 0. So your equation has been simplified into this part equals this part. Simplified. Doesn't look so bad, eh? Okay, let's do it. Half 75 velocity 1.5 squared plus mgh 75 kilo 9.81 kali 150 meter. Betul betul lah kot tak betul dia mati je lah kan. Equals setengah 3 kilonewton per meter. Convert don't forget 3000 x squared. Determine the required unstretched length. Unstretched length. Okay. This is stretched, okay. This is called elongation. Elongation. So let's calculate this one 84.38 plus wow, this is a lot Where is the engineering symbol This one This one is a lot. 110363 equals 3000 bagi 2 1500 x squared. So x berapa? Plus 84.38 bagi 1500 bagi 1500 am I right? Bagi 1500 kan. Remember to square root. 8.58 meter. This is the elongation, okay? So bila dia drop, dia ada original spring punya length dengan elongation. So dia ada dua part kan. This is the elongation. Ini original spring L0. This is X. So L naught berapa? X berapa? We know the elongation is 8.58. So total original length 150 sama dengan L naught campur 8.58 lah. So L naught has to be equal to 150 tolak 8.58 141.4 141.4 meter. So you gotta calculate properly ya. Betul ke noh? I guess so. Should be. So panjang kabel. So this is L naught plus elongation 141.4. Okay, next. Banyak lagi problem. Maybe we'll do one or two more. This is a test rig for airplane during a, not a clash, it's a crash. The plane mass is 8 megagram. 8 megagram? 8,000 kilogram. It's very heavy. Hoisted back up until theta is equal to 60 degrees. And then final punya ni dia akan jadi 15 degrees. Okay. Why 15 degrees? Betul lah, baru ada impact. What is the maximum tension in the, macam lebih kurang tadi je ni. Lebih kurang tadi je. 60 degrees and 15 degrees. So let's just check. Okay. T1 plus V1 equals T2 plus V2. Original kinetic energy ada ke? I don't think so. This is 0. Potential energy, yes, ada a lot. Height dia lah. What is the height here? Berapa height? meter. How do you find the height? I think you just have to find angle ada. Okay, let's do this. Like this. Okay, you just have to find this one. Okay. This is H1. This one. H1. This is H2. Yup, you gotta find that one. So ini ada mgh kinetic energy. Everything is converted into kinetic energy lah. So half. Determine the speed of the plane just before crashing. Crashing boleh lah. Interground at 1050 ya. So setengah m v squared plus mgh. So okay, we gotta solve the trigonometry first. We gotta find this height, the difference. So let's draw a proper triangle. Proper triangle. This is theta. This is 20 This is h. What is this? So sine. 20 sine theta is equal to h. Sine theta is equal to h over 20, right? So okay. So the difference in height, delta h, is 20 sine theta minus 20 sine theta 2, or 20 sine 60 minus 20 sine 15. Correct? Yeah, this is the difference in height. If you guys are confused, I gotta draw it again. Let's draw it again. So this is the height. Let's take here. Our reference, let's take here. This is this height. This is this height. So the plane dropped from location A to location B. What is this height? This is the delta H. So I should rephrase it another way. I think this one is slightly higher, right? So not 60 degrees. You have to minus 15 degrees kot, minus 60 degrees punya, baru dapat besar. Right? Are we okay? The term is here. 20 sine 15, tekan dulu. 20 sine 15. 5.18. Tolak. Oh. Twenty sine 15. 5.18. 20 sine 60. 20 sine 60. 17.32 lah. Okay, so why is this longer than the other one? That height. Sine theta. Okay, sine is all wrong. This is actually not sine, right? This is cos. This is a mega mistake. No longer a small mistake. This is a mega mistake already. Why mega mistake? Because I don't have you guys to correct me. You gotta use cos. This is adjacent yeah. Okay. So you got to change. Use cos, not sine. Cos. Delete everything. Cos. This one also wrong lah. So 20 cos 15. 20 cos 15. 19.31. 19.32. 20 cos 60. 10. 19, so dapat 9.32 meter. So kalau kita ambil datum kat sini, H is equal to 0. This one is gone. Okay. You take this location as H. This one is gone lah. So, now we can plug in the formula. MGH, berat dia berapa? 8 megagram. 9.81 kali height 9.32 sama dengan half. Hey, mass pun boleh cancel kan? Cancel mass. Never mind lah, put it there lah. 8,000 V squared. So 8,000 boleh cancel off. 9.81 times 9.32 kali 2 square root 13.52 meter per second. Maximum tension developed in the supporting cable. This one we have done before, remember? F normal is equal to MA normal. F normal is equivalent to mv squared over r radius. 13.52. Check the answer. 13.5. Nothing much lah, but you have to understand the change in height. Delta H, change in height. Another exercise. Yeah, this is a spring. Toy gun. So potential energy from this spring quite high, 2 kilonewton per meter. Unstretched length is 100 mm. Okay. So dia cakap unstretched length dia adalah 100 mm. Originally spring ni panjang dia panjang ini 100 mm. Nampak tak dia dah compressed? It's already been compressed by 50 mm. So dia punya X is equal to L0. X is sama dengan 50 lah. This is the elongation. It doesn't matter whether it is elongated or compressed. Spring's energy still remains the same. Compress and lock in the position. When the trigger is pulled, the spring unstretches 12.5 mm. And the 20-gram ball moves along the barrel. Okay. Bila dia release trigger ni, dia bukannya release the whole length kan? Okay, maksudnya spring tu tidak menjadi original length macam ni. Tak. Dia cuma gerak unstretches 12.5 I think this is what he means kot. Dia jadi 50 plus 12.5. So dia jadi 62.5 mm. Okay, this is a little confusing. Never mind. Let's solve it properly. T1 plus V1 equals, I know you can look at answer, right? But there's no challenge in there. Do it on your own. There's no challenge in looking at the answers. When you are learning, you gotta do it on your own. T1 plus V1 equals T2 plus V2. Why don't I do this at the top? Any kinetic energy at the bottom? Nothing, 0. Potential energy, yes, half kx squared. Any kinetic energy, yes, setengah mv squared. So in final condition, spring tu masih ada energy lagi sebab kita punya spring ni unstretched sikit saja. Okay, never mind, let's check it out. Spring's original potential energy setengah K berapa? 2 kilonewton per meter. 2000 X elongation 50 mm. Right? So 50 times 10 to the power of negative 3 squared. Ini original springs energy. Bila kita release sikit 12.5 mm ni kan, kita akan nampak half mass of the ball, 20 gram. 20 times 10 to the power of negative 3 jugalah. V squared you don't know. Tapi elongation lah akhir kita. Okay. Remember this one. Ini adalah L0. L0 berapa? 100 mm. Okay, ini kita compress dia. Jadi berapa? 50 mm. So X ni kat sini, elongation dia adalah 50 mm. This elongation kita letak kat mana? 50 mm ni kita letak dekat sini, original. So finally kita release dia kan. So bila kita release, spring ni sudah jadi macam tu, 62.5 mm. So you tell me berapa banyak energy lagi dia ada. X2, X1, we call this X1 X2. So 100 tolak lah 62.5. 100 tolak 62.5. 37.5 mm. This is the final spring energy. This one, baby, you gotta put it here. Setengah 2000 2000. I don't have space I'm gonna write down here 37.5 times 10 negative. Not enough space also. I gotta write everything down here lah. Plus half K 2000 X 37.5 times 10 to the power of negative 3 squared. There you go. So berapa jawapan? Simplify the whole thing. Kira lah. 50 times 10 negative 3 squared kali 1000 2.5. 2.5. Why is it shaking, It is shaking. Never mind. Okay, 2.5. Are we okay? Sama dengan, how about this one? 50 exponent negative 3 squared times 2000 bagi 2. Betul lah, 2.5. Next one, 20 exponent negative 3. Bagi 2. 0.01 V squared. Okay, 0.01 V squared. Second part, how much? 37.5 exponent negative 3 squared kali 1.4. Kecilnya 1.406. 1.406. So 2.5 minus 1.406 divided by 0.01 is equal to V squared. 2.5 minus 1.406 bagi 0.01 square root 10.46. Velocity sama dengan 10.46 meter per second. This is the velocity of the ball. Betul ke tak? Yes, betul. So there's no way you can really understand just by looking at the solution. You gotta listen to me talk. Okay, so you can design things like this lah. So remember, all these things are things that you can calculate. Please use this in your machine designs, final year projects, whatever the thing that you can calculate. So you tell me, how to calculate this using summation of F is equal to MA? I think can also lah. But you have to use a different thing lah, something called impulse and momentum, you'll learn later on. But using energy method is simple, easy. So many exercises. How many exercises do we have? Balance. How many have we done? 1, 2, 3, 4, 5. 5 exercise. 1, 2, 3, 4, 5, 6, 7, 8. Banyaknya kan. The good thing is this is spring, almost the same lah. Spring. How about this one? Also spring, and it travels. This one is slightly different. It has 500 Newton. You gotta change, check how much. Okay, so this one is slightly different. 500. Resolve it. This is the this one is slightly another method. Slightly different method. This is looking at work done. This is looking at work done. You can read through lah. They'll do more in tutorials. Alright,